certain European time. 18 people, we can slowly start. Let me have a short recap about what we taught yesterday. At first, my colleague Jiang talked about the parallel computing. Please. Yes. There are two types of parallelism, that is multithreading for this machine with shared memory, and multiprocessing for the machine with distributed memory. Yeah, that's two kind of parallel is well supported for traditional programming language, for example, C and Fortran, which is suitable for this computational intensive task. But for Python, because of the global interpreter lock, it was not supported for the parallel programming at the beginning, but things changed over time. Now we can use NumPy. More pertinently, that is the NumPy for Pi module for this cross node parallelization. This NumPy for Pi module supports both the point-to-point and also the collective communication between processes. For example, you have noticed about the send and receive. This is for the point-to-point, and for the bcast, for the broadcast, collect, gather, and also the reduce. This is for the collective communication between processes. And I hope that you have got something interesting from the lectures and from handout classes. And if you have issues about this part, also leave the notes for the today's academic document. It is I will share a little bit later. Yeah, this is about the parallel computing. And I mentioned that we have an additional episode about the parallel computing too, with more lesson materials and exercises available here. If you are quite interested and take time to go through these materials, there are even more choices for you to do this parallel computing. Later, my colleague Ashwin talked about the benchmarking, profiling, and optimizing. I should say that the modules I mentioned before, I mean, multiprocessing module, the concurrent module, and the MPI4Pi can only guarantee that you can use these modules for the acceleration. But once you port your code from a single CPU version to a multi-CPU version, either using multiprocessing or MPI4Pi, the first thing you should do is to make sure that the multi-GPU version works well. And then you take time to benchmark the code to find the bottlenecks. And for there are several choices. For the simple code, you can use the magical commands like time and timemate for this benchmarking. For quite a complex code, you can use built-in profilers, for example, C profile or the line profilers for this benchmarking. Once we can identify the bottlenecks of this Python code, we need to make the corresponding code to go faster. That's the code optimization. There are several methods like algorithm optimization, CPU and memory optimization. I should say that how to optimize the code to get a better performance is really project dependent, as my colleague Ashwin mentioned yesterday. It depends on the size you are going to handle, and also the frequency to call the function and the frequency for the data I/O, input, output. It's hard to say which is the best, but try more possibilities and you can find the optimal scheme for your project. Besides this optimization method, we can have more strategies to boost the performance of the Python code. So today, in this morning, in the first episode, we come to a new episode about performance boosting. We talk about performance boosting. But before talking this, let's go a step back to see what is Python. Python is an interpreted language, which means that the Python interpreter reads and executes the code line by line. It directly translates the code into actions without generating a separate executable file. This is totally different to the compiled programming language, for example, C and Fortran. Such interpretation has advantages and disadvantages. For the points, is the dynamic typing. For example, you can assign the integer 1 to 3 to a variable x, and later you can assign another string, for example, hello world, to this variable. And rapid prototyping, yeah, quite you can no compilation, so execute the cycle, so you can speed up to write the code. And cross-platform, if the interpreter is available, you can directly run the code. And a big thing for Python is that it can automatically handle the memory management. So that's not necessary for you to handle this. If you use C, you have to allocate memory before you use some arrays matrix, and also after that you have to release the allocated memory. Otherwise, you will get the memory leakage issue. This is quite severe. But for Python, there are also some cons like less secure and debuggable. This is related, as I mentioned before, at the beginning, you can assign an integer to a variable, for example, x. Later, you can assign this another string, but when you debug the code, you have to go back to see what is a point to. It's an integer, it's a string, it's a list or tuple, something others. And for Python, the significant thing is that the slow execution because the interpreter translates the source code line by line, which add an extra layer of overhead and complexity when you run the code. Nothing's the resources intensive. Usually for the interpreted language, it consumes more energy and the CPU power compared to the compiled language, for example, C. All these advantages and disadvantages come from intrinsic interpretation of the Python code compared to the compilation process of, for example, C code. Here is a general descriptive about the compilation process of C code and compared with the interpretation of Python code. For the C code, there are 4 phases for code optimization from the source code to the executable file, preprocessor, compiler, assembler, and also line linker. For the preprocessor, it includes the removal of comments, expansion of macros, include files, and also the condition of compilation before you compile the code. And the next step is a compiler. You will compile the code to produce intermediate output file. This is the assembly code. It contains the assembly level instructions. Then come to the third step is assembler, in which the compiler will assemble the obtained intermediate assembly code to objective files like this. In these objective files, it contains machine level instructions. The last step is the linker. It links all function calls and generates executable files. For example, if you use Windows, it's the exe file. You download from the site, you click the mouse, you can install this package. This is the simple description of the compilation process of C code. However, for Python, it is distinct, and there are generally 3 steps for a Python interpreter to do. First, you should have something like a compiler. It's also something like this. And next, use this compiler to compile the Python code to bytecode. There are several small steps at this phase, but for example, argument parsing and also syntax analysis. And once this is done, execution of this bytecode using the Python virtual machines we call the PVM. PVM is kind of interpreter that read and execute the bytecode instructions one by one, which means that each instruction is fetched, decoded, and executed sequentially. And because of this, the Python code has a very slow execution. If we compare these two processes, you see that the C compiler compiles the C code to the objective or executable files. So can Python code borrow this concept to improve the performance of the code? A short answer is yes, and it is the pre-compiling Python. So what is pre-compiling Python? It refers to a process of the converting the Python source code, the files with this .py extension, into the bytecode before the execution. The bytecode is an intermediate representation of this Python code. It runs more quickly than the raw Python source code. There are two representatives we're going to talk today. This is the Cython and also Numba. Both of them have a very good support for the NumPy arrays. We come to Cython first. So Cython is a superset of Python. It can not only call the functions in Python code, but also can call this function in the C code. It also supports the declaration of C types on variables and also class attribute. So with Cython, source code can be translated into optimized C code. And also some code are compiled to a Python modules. So it's a mixture of C code and Python modules. And because of this, we can get a very good performance of the code. How to use Cython is quite straightforward. You can just use this Cython and 2% signs before the Cython and using this magic command line, magic command in this cell, and then you can run this. Sorry. Okay. Yeah. In Jupyter Notebook, you can see how we use this. This is quite straightforward. So I'm going to use this Jupyter Notebook for the demo. So this is a straightforward to use it. Here we try to solve a problem about this integration. We have a function x squared minus x, and in this problem, we try to integrate this function from a to b with a step size of dx. Yeah, we have several steps where we go from the pure Python code to the benchmark, and then use Cython to see how can we include the more command from or gradient from Cython so that we can gradually improve the performance of the code. Before that, we should have a benchmark using Python. This is a step 0. The code is available here. So you can see we defined three. We first define this function fx. This is this one, x squared minus x. Then we have another one, integrate this function fx from a to b. A is the from a to b. N is the number of steps from a to b. So dx is the step size. I mean, how many steps we're going to go from A to B, and we can determine the step size. And then integrate. But this is just one integration. One integration runs quite fast. We want to do more. We want to do more integrations simultaneously to see the performance of the code. Therefore, we defined a third function like this, apply integrate. We have input. This is the column A, column B, and also column N. For each one has the value of A and B and also N. With the third function, we're going to handle lots of integrations from each A in the first column to each B in to the second column, and with the number of N in the third column. Yes, and these three functions are well defined. We need to integrate. We need to use the pandas to generate data frame, and then we pass this matrix to call this function. Let's see how it works. I just for me it's just copy paste from the web page to the Jupyter notebook. So I just click this. It works, and we generate this data frame. We see what is this. We have 1,000 rows and 3 columns. The first column is the value of A, second for the value of B, the third one is the value of N. N is the number of steps from A to B. Then we do this integration. We use template to benchmark this function to see what will we get. Yesterday I made this run as 194 milliseconds, and now it's 200. Okay, quite close. We can say that 200 milliseconds is the reference for us. When we see how can we improve the performance of the code one by one. Step 1, we use Cython for another benchmark. So before we use Cython, we need to load the Cython extension. It is here. I think I have loaded this. See, yeah, the Cython is already loaded. Therefore, that's not necessary for me to load it again. But when you first load the Cython extension, there's nothing for it to happen. And for this Cython, we need to add a magic command -a for this annotation. If we don't have this, you can see nothing about this compilation. Let's make this. I remove this -a from here. I click this button. It's done. If I add a -a here, I can get something more. Yes, you can see generated by Cython 3.0.11, and the yellow lines hint the Python instruction. Unfortunately, I cannot see this yellow line from here. But if I use VS Code, it is here. So let me save this, then I can see this. Yes, you can see. You can see these yellowish lines. Almost all these lines are yellowish because yellow means the Python instruction. These are the Python code. The task of us is to remove this yellow as much as possible so that we can improve the performance of the code. If in addition, if you click the line started with add sum, you can see the C code generated from Cython. See, I think it is this one. Yeah, this is the low level C code. And this one, you can get a fast computing about this function over some part of this code. Okay, at this step, we do another benchmark. At this step, we did nothing. We just use Cython instead of Python to run this code. So we will see what we can get about how long we can get about to run this code. 140. You remember that if we use Python, it's 200. Now it's 140. The time is 70% of this time used by Python. This is a kind of acceleration. 140 is 140. 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 Seems good, and we can do more. Step two, we add some data type annotation to the input variables. If you see it here, for this function, we have input variable x. For the second function, we have a, b, and n. For the third one, we have a column a, column b, and also column n. We can use data type annotation to explicitly declare the type of these variables. Here, double means that double is the C type identifier, and this is the later we're gonna have a comparator like this, and it's also for this float 64 in the NumPy and also SciPy, and also not SciPy, it's Cython. And for this one, there's a double type. Double type is the long time. It is int 64. And you see, we at this from step one to step two, we change nothing except to declare the type annotation from here. And yeah, seems run this code again, and also generate the similar. And I will if you use VS Code, you can see this yellowish, where this some of them are quite yellow, some are light yellow, means that the less Python interactions. We run another benchmark to see the step, to see the time it will take. Yesterday I got a 64, now I got a 65, 66. Well, from 200 to, let's say, 240, and then 66. Again, we have a good improvement on the performance of the code. But actually, we did nothing the first way from Python to Cython, and then add some data annotation, data type annotation to these input variables. You may notice that here we use the C type identifier, double, long, and for this C type identifier that are consistent with that of the Cython type identifier and also NumPy D type. If you here, this is the long for this NumPy of int, Cython and P is int T, quite strange like this. And for the float type, we use double. This is the float 64. And it can be float by default, but it's actually the 64. This is the double precision for this NumPy. And the two things we should address is the how to import NumPy or SciPy. Here, use import NumPy as MP in the Python, and we use in Python you should use this one. C import NumPy as CMP, just include C before the import and MP. What's the difference? Import gives access to Python instructions or attributes. C import means give to C functions and attributes. And usually we combine import and C import together as Cython can handle internally, handle these two meanings. Yeah, from step two to step step two to step from step one to step two, we only add the data type annotation to the input variables. We can get another improvement. Let's move on to further to add the data type notation to functions. You see right here. There are three ways for the declare functions. Def, this is the Python style. The defined function can be called by Python or also Python. Number two, cdef, or the C style. The defined function can be called from Python and also from C, but make sure that this is cannot be called from Python. Number three is cpdef. It's the mixed style of C and Python. it combines both def and cdef. Here I'm in the combination, not only for the declaration, but also for the performance. Here, see, cpdef function may be as fast as those using cdef and might be as slow as def declared function. So you might get this sometimes might be slow, some might be fast, depends. Yeah, that's it from this part. Yes, for one thing is here. Yeah, for CDEF, it usually gave the best performance, but implementation that this time the code is C code. It's not the Python code. Yeah, we make the changes on the code. You can see these lines are quite highlighted here. For this first one, we use CDEF because you can see we just have one line in this function, and this is you can say this is a C code, quite simple. And the second way is the cpdef, mixture of C and also Python declaration. Because in this function, some code can be seen as C code, and some can be Python code. Once you compile using Cython, you can see which line is yellow, which line is white. Yellow means this line has Python instruction. White means that's the C code. Third one, we use cpdef because the code is also a mixture of C code and Python code. And after the addition of data type annotation to functions, let's perform another benchmark on this. Number 3, yes, we are here. I will see. This is the step 3 to see from here. Step 2, step 3. You can see this is the light yellow, means that this might be a C code, and of course, for the yellow means this the Python code as a mixture. At least this here is the mixture of C code and Python code. We see the performance of after we change, after we add the data and type to the functions. Previously it was 66. Okay, again we get 8 millisecond acceleration. Now it's 58. Seems good. Can we do more? And we can do a little bit more. There is one thing I should. Oh, sorry. There's one thing I should notice, that we can also add the data type annotation to local variables in this inside the function, and also even the output. This we are going to handle this as a step 4. You can see nothing changes, but use another name for this function. It's okay. But here we use cdef double to declare the type of these two variables, s and dx. Double means double precision in for this C type identifier. Here we use long, means for the long time of this variable. This should be integer. And for the variables in the third function, it's the same. We use the long to declare the type of n and I, for double precision to declare the output race. Okay, and changes. Once we changes, we again perform the benchmark on this version to see the performance. Number 4, it is here. And we run this. I got this yesterday. Let's see how many milliseconds I can get from here. 14. Okay, seems good. Okay, from step 0 to step 4, we know that step 0 is a pure Python benchmark. It's 200 milliseconds. Step 1 is Cython benchmark. Just use Cython to run this code. It's 140. Now it's 14. We have 10 times faster acceleration than the original Cython implementation. If we see the code from the VS Code at the beginning, we can see here step one is what is this is the benchmark using Cython. It's fully yellowish, almost all lines here. But if we go to the last one, you can see these are the white, means these are the C code, and also here. So which means that we can figure out we have less yellowish lines right here. This is true as our target is to remove yellowish as much as possible from the Python code. That's which means that less yellow and means more efficiency in the performance. That's is what we're going to do to improve the performance of the code. Yeah, we come to this step 4. Can we do more? What should we do more further to improve the performance of the code? If yes, how and what to do? I don't know, but I leave this question to you, and you tell me how can we further to improve this code. Let's take 15 minutes to play with the code. 175, 159. Well, super good. You can see that from step 0 to step 1, we just use Cython instead of Python, and we can get 1.3, 1.4 times acceleration from the code that from the time it is kind of 7% of the time from the Python code. From step 1 to step 4, we gradually add data type annotation to input variables, to functions, to local variables inside the functions, and the output. We can gradually increase the performance of the code. Okay, it is 9:50. Welcome back. Let's move on to the second part to talk about the number. So, what is Numba? Numba is an open source compiler. It's called just-in-time compiler with JIT that translates the subset of Python code and also the NumPy code into the faster machine code. With these numerical algorithms in Python code, it can approach the speed of C and also Fortran after we call the compilation using Numba just-in-time compiler. This is good because we can significantly increase the performance of the code. The usage of Numba is quite easy. You don't need to replace the Python interpreter. For you, what to do is just to add the decorator at JIT before the function that we use the just-in-time compiler to compile this function. It should be noted that the just-in-time compilation will add some kind of overhead to the runtime, but this is just for the first time we run the code. Once the functions are just-in-time compiled and catch it, subsequent calls will be quite fast. Another thing is that Numba support the compilation of the Python code to run on both CPU and GPU. We have a separate episode about the GPU programming. In that episode, we provide some examples to run the Python code using GPU. For those you can access to Lumi, try that code, and this I think it's a very good opportunity for you to use GPU for this programming. If in your personal computer you also have the GPU, try it to to run this code and to see what if you can get more benefit, you can get a further improvement about this code. Okay, let's work on the same problem about the integration of this function x minus x squared minus x and integrate this function from a to b. And as usual, step 0, we should do the benchmarking, but we have done this before, so there's no necessary for us to do it again. Even you can run this code. I have this one. You can run this code again. The time is almost the same as the previous step. So we skip this one. We just move to number. We add the decorator at JIT for the functions. For each one, if this is the Python code, you just add to the add number.JIT before each function, which means that we are going to use JIT compiler to compile this function. Somewhat easy, right? And if we run this, I will clean this. Oh, I should do this from the beginning. Step 1, 205. Remember last time we got a 200 millisecond, and the 205, well, almost the same. For step 1, we run this code using NumPy to see 0.5 millisecond. Okay, if it's kind of faster than the last one we got from the Cython part. Which means that if you're going to Cython, you have some space to improve the code performance. And again, we can do more. We can add the data type to the JIT decorator, step 2. And here you can see for this number float 64, this is for the double precision in C, but this is for the output. In the parentheses are the data type for the input. This is for the X. This is quite clear for the second function. This is for the output, S times dx. And the data type in the parentheses, float, int 64 are the data type for A, B, and N. And accordingly, you can add the corresponding data type to the third function, and to see everything is, we do another benchmark to see. See, here is 475, is 484. Well, no, it's almost the same if you consider the error bar here. So I can say that even you include the data type to the functions, seems that we did not get any improvement right here. But well, it's still very good. It's an opportunity for you to see what we can do right here. Can we do more? And we have just 2 steps. Can we do more? Actually, I don't know, but we can take time to explore more possibilities to improve the performance of the code. And can you use cdef right here? Try these possibilities yourself, and you can gradually to see how to improve the code performance of the code. Until now, we talked about Cython, we talked about Numba. You may wonder which one I should use for my project. Well, it really depends. From the performance perspective, both Cython and the Numba will get the similar result, depending on the specific version of Cython, Python, Numba, and NumPy. Usually, you can get the similar results. From the practical point of view, NumPy is generally easier to use. You can see that you can just add this add number to JIT, maybe more data type right here. before the function, which means that we are going to use the just-in-time compiler to compile this function. For Cython, it is you have to use the more to add the data type annotation to the local variable, to the input variable, to the function, and also to the function. But you can clearly see the gradually increase of this performance. For Cython, it is kind of stable and mature, but NumPy is developing quite fast. Another thing that the NumPy also supports the GPU programming. If you can access the GPU card, and maybe you can use by NumPy. This is you can try the CPU version first, and then see if you can further improve the performance using GPU programming. The interfacing of NumPy and Cython to C code, you can see that Cython can compile arbitrary Python code and directly call C libraries, but NumPy has restrictions. So in your research group, if you have a lot of C code from colleagues, from supervisors, that's not necessary for you to write anything. What you should do is just use Cython to call these libraries to save lots of time. And based on this, you can see how to improve improve the performance of the code. Okay. In one sentence, if you perform quite simple operations on small data, I mean small data as a kilobyte with some megabyte, NumPy or maybe sometimes together with Pandas and SciPy is enough for you to handle the data. If you work on large data and quite a complex data, a mixture of images, audios, videos, and the text data, you can choose either Cython or NumPy, depending on your project, as both Cython and NumPy can give you a very good acceleration of your code. Again, hands-on exercises. Here we have 4 exercises. The first one is the word autocorrelation code. You might played with the code yesterday, but we will step further using NumPy to explore the acceleration. Number 2 is the calculation of pairwise distance in the dataset. You can choose the tool you like. You can use NumPy, you can use SciPy, you can use the Cython, you can use NumPy to see which one you can get better performance out of the code. Number 3, bubble sort. This is the classic problem in the programming, and it is sort the values in the array either from small to large or from large to small. What we want, we get a new array. This you can design algorithms to see how the algorithm the performance of these algorithms. Number 4 is about the calculated square of an array. We have an array right here. Here we provided a few different versions using NumPy. This is a NumPy version, the NumPy without static typing, NumPy with static typing, and additionally with the vectorization. Benchmark this code and to see which one you can get the best performance. Yes, I think I will stop here and let's again play with the code for 15 minutes. 30. Welcome back, everyone. We can continue to a new episode about the Dask for scalable analytics. It will be given by my colleague Ashwin.
Thank you, Yongle. Do you hear me?
Yeah, it's clear.
Okay, great. So welcome everyone to this last session of this course. So we've gone through a very wonderful journey, like describing all the tools and libraries which help you efficiently do computing. So we have, just to recap, like we have talked about parallel computing and where we saw some ways to parallelize your data, your computation, and that was done through mainly multiprocessing, uh, multithreading, and MPI. Uh, but just to give you a context, like once you do that, the plus side is you get very good efficiency in parallelizing this way. But it goes down to the developer to think about how will you divide your data. It's all about divide and conquer, but then you have to think about how will you balance it properly so that each process or each thread gets a good load of work and they are not waiting for it to happen. That's one downside of this approach. And the other downside is once the code is parallelized, it's very hard to go back to the serial uh, state. For example, if you're thinking of doing debugging, you might have to find ways to debug in fully parallel code, which is not easy. It's less of a problem in Python. Sometimes you can do debugging still with just single process. Even though the code is parallel, you can try to make it run sequentially, but it's a bit harder when you use these approaches. So what if there was one way, one single way that runs in your laptop, even sequentially or even like with two cores, all the way up to really big super computers. So that was the idea behind Dask. So Dask was designed to make it easy to parallelize common computation workflows. Uh, so we will see like what kind of workflows you can do with Dask. It does in a slightly different approach, which involves something called as lazy execution. That's also something we'll see. So just to give an overview of this session, I'll be explaining what Dask is, how it works, the concept behind Dask clusters, and then we take a look at three different data structures which exist in Dask, which might be really familiar to you from the previous episodes: arrays, data frames, and bags. Then we'll go into an exercise, slightly long exercise, where you can pick and choose what you wish to do. You don't have to do all the questions if it's too much. Once the exercise is done, we look at a low-level Dask primitive called delayed, and we round it up with some comparison to another library called Spark. And finish off with the final exercise, which uses delayed and a very practical application of Dask with Xarray. So that's it. Let's take a look. And yeah, just to remind you again, like keep the questions coming in HackMD. I'll keep an eye on it and then we'll answer it once the session is, we go into a break or a, no, we go into the exercise. I'll try to answer it or my colleagues will answer it. So yeah, once again, like modern computational workloads can be really big in volume, and you may not be able to run large volumes of data in a laptop. For example, if you can think of something like a really big climate data set, which might be easily hundreds of gigabytes or even more. And then if you're trying to do some analysis on top of that, you cannot load all the data in your laptop. So this is also something which is called as out of memory computation, which is tricky to do it by hand, but Dask tries to make it easy for everyone. So Dask gives you the tools to run something on a laptop or to even scale it up on a HPC system, a supercomputer. And Dask can also make use of multiple CPUs, which lets you parallelize. So how does it work? If you think about MPI, you have to manually, if you're given an array and if you're supposed to do a sum, then you will have to think about how to divide the array and then do the sum on each layers of an array, and then finally sum it up again. So you'll have to do that manually. But in Dask, there is no concept of doing this distribution, uh, doing a fine-grained distribution. Dask abstracts away all the parallelism in terms of task graph. So in Dask, there are two different components. One is this task graph, which does the scheduling. No, sorry. So one is the scheduler, which takes the task graph and then executes it. But the scheduler does not have to know how to execute it. Like it is just a pool of processes waiting for some task to happen, like to receive a task, and then the result will be sent back. So in that way, you can represent any kind of computation, not just limited to arrays, even calling writing to a file, for example, or like iterating through different rows of a data frame. Or you might have a really big JSON file which does not fit in any of these array data frame, which is like a big dictionary or a big list, which you can represent using Dask. And then you write your code, it builds up a task graph. You have to initialize a scheduler that you want, and these two combined will do the computation. I know that's confusing, but I think it will be more clear once we do the demos. So a little bit about the cluster, which takes care of the scheduling. The default cluster, and the most common way to run is using a local cluster. The local cluster, as the name suggests, it looks at the current environment, and it can scale up to maximum the number of threads, or the number of cores it has. But even if you're using a local cluster, you can choose different types of scheduling. It can be based on multithreading, if you choose threads, multiprocessing. It can be synchronous, which will be like sequential execution. So you'll have a single thread, and it's useful for debugging. But if you want to scale to supercomputers, that's also possible. So if you have a Slurm job running in, let's say, Lumi, and then you want to launch these jobs through a distributor across multiple nodes, then you might need to use distributed. But we won't be looking so much into that. But the distributed type of scheduling comes from a plugin to Dask called Dask Distributed. And that's something you install on top of it. But even if you're not using a supercomputer, you can still use it because it's much more sophisticated. It has lesser latency, and it gives you very nice features, like you can visually look at a dashboard to see how the execution is happening. There are other options as well. You can use a Slurm cluster, which I think I haven't tried this yet, but if I remember correctly, you run it in your login node, and the Slum cluster will be like submitting jobs for you to run this execution. And if you want to do it on cloud as well, so you can have the same code which works in Kubernetes. So that's also possible. So because it's so high level, you get many different ways to set up Dask. And yeah, I'll start by demoing. So the easiest way to set up Dask is to use Jupyter Lab, where you get uh, where when you install this Dask Lab extension package, which is already provided in our course Conda environment, you get this beautiful icon in the sidebar. So we go to this icon and then scroll down if it's too thin, and then you press new. Then it spawns a new cluster working in the same environment, which is the local cluster as it is called. Takes a few seconds, I think, to set up, initialize, but once that cluster is set up, it looks like this. It will have two servers running, one which takes care of the scheduling and one to monitor it, which is called the dashboard. And then you get this button, which I'll show you soon, to inject the code so that you can interact with this cluster with code inside Jupyter. You get something like this. And there is also another button to scale and shut down this. Scaling means you can increase the number of cores which are assigned or you decrease it. Increasing the number of workers. For example, if you're using threads, you can use many more workers, but the default is to use multiprocessing in Dask. So here my cluster is spawned. I press this, I get this code which connects to this scheduler, the client. And either I can press here. Yeah, I think you need to press it here. But let's take a moment to see what is here. So here you get some information on what the scheduler is, what the current memory is, and then you get this button which will spawn 3 widgets, which are quite silent right now, but that's because we are not running any job yet in Dask. Also take a look at this scale option, which is can choose the workers. I don't know if I can, maybe you can scale it more, but let's try it. Yeah, you can increase the number of workers, oversubscribe it, but I only have 4 cores, so I'll try to keep it simple. The alternative is to use adaptive scaling, so choose the minimum and maximum workers. So that's how you initialize the Dask scheduler. All of this can be done with code as well, because sometimes you won't be running a big simulation or a big computation using Jupyter Lab all the time. You need to script it, and then you can do that as well. So one way is to manually choose which cluster you want and then give it to the Dask client. Or just let Dask choose it for you. And then usually it's the same thing, the local cluster with processes as true. You can also limit the number of workers when you are doing this initialization of local clusters, how many threads you want, how many memory it should consume so that it doesn't blow up in memory. Otherwise, it will the memory level will be the maximum. Why is processes true a good choice? Because we are, after all, using Python. Uh, and as we have noted in the previous episode, there is this global interpreter lock. So with threading and particularly with CPU bound computation, you might not get good parallelism if you could use threading. So to start with, always processes equal to true is a good choice. And this is how you adapt and scale your cluster. Uh, right? And once everything is done at the end of your script, you might want to do this client shutdown to ensure that everything finishes cleanly. Or the alternative is to press this orange button on the sidebar. So those are the what powers Dask. But as someone who develops code or does analytics on some data, you want some way to help Dask understand the data and then build a task graph on top of it. So if we are dealing with NumPy arrays, the way to approach that is to use Dask array instead. For Pandas, it's Dask data frame, and for mixed, data like very messy, irregular data, you can use Dask back. So the mantra behind the Dask developer is to not reinvent an API. So you will quickly see that uh, the syntax for Dask array, even though it's a different library, it's very similar to NumPy, and the same goes for Dask data frame, very similar to Pandas. So they copied over the syntax as much as they can with some extra sauce on top of it. So yeah, here it's mentioned how Dask is very similar to NumPy array. Uh, so Dask, like we mentioned in the beginning, it uses something called lazy execution, so that it only computes when you ask it to. So let's take a look, like comparing NumPy and Dask side by side. Uh, so here we are building. Sorry. So here we're building a NumPy array, which is 1000 by 4000. Oh, sorry, scroll too fast. 1000 by 4000 big, and then okay, this is better, I think. And the same, in a similar syntax, we build a Dask array. And then it says once, but it doesn't show any data yet because it builds a graph, so it has not really allocated this array yet. So this one has only one chunk, so that if you start to do any computation on top of it, it will be given to a single Dask worker by default. So if you want to make sure that this will be parallelized, you want to pass this chunk shape to tell Dask how to split it. So that's how you do that in Dask. Huh. Oh, that's a bit strange. Now, why would that be one chunk? Did I miss something? Let's try to reduce it further. Okay, I don't directly see it. But anyway, going forward, like if you do this sum on NumPy, you will get the answer immediately. Whereas in Dask, ones.sum, you don't get it right away. But because you are trying to do that in as a graph, a task graph. So in order to do that, you can call something called visualize method. So I'm trying to do this approach to add visualize. It will show you how Dask intends to compute it. Uh, so I'm not sure why it was not divided in terms of graph, in terms of smaller subarrays. But if it was divided into subarrays, you will see different branches coming together and getting a sum, and then aggregating it. And finally, like here you have the visualization. And when you do compute, only then it does computation. Oh, access is 0. Did I do something wrong here?
Using Lumi on your personal computer.
I'm new on Lumi. Is that the reason?
I don't think so.
Did this change some way when oh, I'll try to quickly run this again. Maybe it helps using the same task cluster. Mhm. Access it. This should be very trivial. I don't know why. I don't see it. Okay, I didn't change the chunk shape here, but that
I'm
was
trying to follow the same on my local cluster, and I'm getting exactly the same errors. So it's probably not cluster dependent.
okay. Thank you for checking that. There is also shape device. Maybe this what is it? This keyword argument is not accepted anyway. Like it was passing into the keyword arguments, and it doesn't mention that anywhere here. Wow. Another way to do that is like this. Rechunk, does that help? Okay, so you could do like that instead. Maybe this is an old way of doing that. So if you do rechunk, then it divides okay, this is a very small chunk. I'll try to use chunk sizes of 100 by 100 arrays. Is it too small? Maybe 1000 by 1000. So that is not too complicated to visualize. Okay, it doesn't show that, but at least we hope something will happen here. Okay, so you need to have some chunks to make this work in a distributed way. But at least we saw something happen, and then we get back the sum. Okay, so we need to fix that. We need to use rechunk instead of settings passing chunk shape. Someone had an issue with the Dask setting up the Dask client. Nani is some library which Dask uses in the background. So maybe a little bit more description of the whole error might help. My colleagues might be able to help you with that. Otherwise, feel free to ask them. Okay, that's a little bit about very brief description about Dask arrays. Now over to data frame, the equivalent of Pandas data frame. So you might have a very big CSV file which does not fit into a memory. You want to accelerate some kind of aggregation using multiprocessing or multithreading. So that this is what Dask lets you do it. So here is an example. So you might be starting off either with a Pandas data frame first. You ask the Pandas to load it for you, and then you can, in principle, drop into a Dask data frame, convert it. That's one approach. And you specify how many partitions that you want. The alternate approach is to use Dask to do the reading for you. The syntax is sometimes different. Like, for example, index column specifying along with read CSV is not supported. So you need to set the index later after the reading is done. And instead of specifying how much partitions you want, you can set by how much is the partition size or the block size as it is called. So you can set it in terms of megabytes, like, or kilobytes if it's that's not the value that you're looking for. Or you can let Dask choose it for you. So I'm gonna try this one here. So I'll remove this part so that I only demo one. And I'm going to choose the block size approach. And let's see what Dash thinks is a good number of partitions based on the current. Oh, okay. Okay, that's not good. Maybe. So maybe I'll try to repartition here. Yeah, obviously this CSV file is not big, so that's why Dask thinks, okay, we can do it in one partition, but just for the purpose of this demo. DDF. Okay, we divide it into 10. You can visually inspect it. As opposed to Pandas, you see in Pandas you will see all the values inside the data frame. But here you only see some metadata, like how many partitions it has, what are the columns, what types you get. So you know that Dask is trying to wait for the computation to happen before it actually reads and does something. So let's try to pass on some computation to Dask here. So here we are trying to create a new column called child, which will be a Boolean, which will be a comparison on the age column. And then based on the sex and child column, we'll check how many people survived and take an average. Okay, we'll try to do this towards the end. I'll call it survived, uh, average survived, maybe. And so to see how Dask is doing this, we'll try to visualize this. So you see like how Dask builds some sort of task graph on top of it before giving you the mean that you want. But it hasn't even read the CSV file properly, or at least not completely anyway. And then, so now we have this computational expression that you want to compute, and then if you fire that, Dask starts rating it, does some computation, and gives you the result. So it's lazy. It tries to parallelize it across 4 workers that I have. And each worker gets a task based on the current load, and Dask does it for you. You don't have to think about how to distribute these tasks yourself. You can also analyze different things here, like how much time each task takes, and then decide what to do. You can also take a look at how the workers are doing. Are they blowing up in memory and so on? So those kind of things you get from Dask, the distributed Dask, some diagnostics. Just a note from HackMD, one learner managed to do this sum example that we showed before, and there was a Dask graph which splits into 4 as it should. But for some reason, I was not able to do that. So yeah, it's not every day everything works. And over to Dask bag. So Dask bag is when you're thinking like lists or a big dictionary, loading a JSON file, or some other Python object which cannot be represented in a structured way. So then you need a collection of data. Could be a big string, which is what we show in this demo. So in this demo, what we are trying to show is like you do some analysis on a big chunk of text, and we use a Dask bag to parallelize the computation. So this is the Python way of doing this, using for loops and string operations. So what we try to do here is there is a word count HPDR repository, which you can get from if you follow this link. You can either go there and then click download if you don't have Git, but if you're comfortable with Git, you can copy this and use Git clone instead. So that's how you'll get those repository. And then once you have that, you can either run the Python version, which reads the file, splits into lines, and iterate over lines, remove some punctuation, splits the line into words again, iterate over words, make it lowercase so that it looks unique. And for each word, it stores it into a dictionary called counts. Increment it every time you see this word. And by doing so, it builds up a count of all the vocabulary it sees in this text. And the idea is to show which word is the most frequent word, or rank it accordingly. Sort it, sorry. So let's see that in action. So I have this already, I think, yes. And then once I go there, I can see this file as well, lstat pg10. There are multiple pages of text, but we'll be just using one page for demonstration. And then I copy this code, put it here. So, I mean, it's not a big text. If you see, it's only 4.3 megabytes in plain text. So that's why it's quite fast. But you can think of something of the order of gigabytes, and then it will take forever to loop through everything. How to do that in Dask back? There is a bug in this code, so be cautioned, but you get approximately the same result. So here, what you'll do is instead of using Python's open method to read it, you use Dask bag read text, and then you do a series of operations which can be inspected in between, but you can chain it into one big task graph and then press compute at the end. And that should give you the top 10 results of words, unique words. The bug is in this filter operation because this is not exactly similar to what we are trying to do here. So as before, it splits the operation and then does it in Dask using parallel workers. These methods are quite similar to, if you would ask me, like Pandas data frame methods. In Pandas data frame also you get this string methods, something which looks like this. So that's one way to learn like what kind of methods exist, but you can look at Taskpack documentation as well. But if you time these two things, like let's look at the timing for this one, how long it takes. It took a few microseconds, but instead here, what did I do? Let's try to do, I think I should have done 2%, so to cover the whole cell. Yeah, that's more appropriate, like 400 milliseconds. It's not too bad, at least for this case, but it's not faster even though you're using many cores. So the reason is it's small data. 4 megabytes is nothing to parallelize. So you might as well run it sequentially. So Dask only makes sense when you are using very big data set and not on small data sets. So now we'll go through, drop into exercise. You can go here and then you can pick and choose which kind of data structure fits into your workflow, which you are more interested in. Do you work with arrays or data frames, or none of those? Then you can try bag instead. So try to do one of these exercises at least, but if you have more time, you can try to do two. So we'll give 20 minutes for this, and then that should be good. And keep the questions coming. We'll try to answer it. All right. Welcome back. I know 20 minutes is not much. It's quite a long exercise, so you might want to try it when you have free time later on. Even I barely managed to do one exercise, so it's all one can do. I just want to point out, and thanks for this. I saw that I was trying to pass set chunk shape as an keyword argument. It should be chunks instead. That was the mistake. When I did that, I got task graph, which splits the array into 4 as it should. So that's that. And here I'll demonstrate the first question, which has to do with the Dask array because it's simple, and the choice of chunk size, which is quite important when it comes to Dask to understand how it works. So here is my attempt at it. So the idea is to do a computation, calculate a mean over an axis along the columns. So here you have a very large array. I removed 1 0 so that it's slightly smaller. And then you can do the benchmarking with just NumPy, see how long it takes. And then you can try to use Dask syntax instead, split it into chunks of, if you just specify integer, it will be a square array. It will try to divide it such a way. So you see that you get a speed up. So because it's split into reasonable number of chunks, something that you can see in a task graph. That's probably the thumb rule. It's faster than NumPy because you're using multiple processes, so that's good. What if the chunk size is the same as the array size, right? And then if you do that, it should work around the same time as NumPy, maybe slightly more because of the overhead of using Dask. But sometimes it can be really slow, so it's not a silver bullet either. But thankfully, because we are using simple expressions here, we are getting the same timing as NumPy. What if you just spam the whole system with numerous tasks? Then the task graph is overloaded. You might get a warning even like, okay, this is a big graph, and you see something like a swarm of hornets, I think, trying to do it, and it takes much longer. So you don't want to choose a very small task graph either, or a very small chunk, or it shouldn't be very big either. So it's must be logom somewhere in between. So that's the lesson learned from the first question, which is about chunk size and using Dask array. Chunk size is or partitions as it's called in Dask data frames are very important when you're using Dask. This question is a bit more applied, like how you would do it in Pandas, and then to see like how uh, the syntax in Dask will look like. So the idea of this question was you have a power law, you calculate the power law, and then you apply it on one of the columns in this results.csv file. Sorry, I didn't get enough time to explain all these questions before the exercise. But here are some hints on how to go about it. But if those are insufficient, there is the equivalent Pandas code. So here we read the file and then apply this function, which takes in it takes in a row actually, not a column, sorry. And then computes some results out of this. The Dask version also looks very similar to this line of code. You see iloc and apply, and then you pass on the function that you want to apply. But the difference is you would like to, set some types so that Dask also knows what is going to happen. And then about Dask bag, it's the same problem that we demoed. And the difference is to just try a big file, concatenating all the text files, and then you get a faster speed up maybe because it's a bigger input. You can also play around breaking the pipeline over here. That is to see what's going on, how the graph looks like, or what you get if you put compute just after this one, maybe, to see what happens until here. So comment out all those and then see. So now we have a sense of what collections are in Dask and how to use them. But sometimes you might have a workflow which cannot fit into these abstractions, like using a collection or a array or a data frame. So then you might want to use something called Dask delayed instead. This can be added as a decorator on top of a function. For example, here, this sleep is added to simulate real work, so that it looks like it's going very slow. So let's try it out. You can follow along if you want. So here I'll copy that code, put it here, defining those functions. And then if I run it, in Python, I will get the results immediately, as it should, because Python doesn't do any lazy computation. But if you want it to be lazy, then we use Dask delayed and create a delayed version of this computation. So this is equivalent to adding a decorator, something like here, something like this one. It's the same effect. So you can either do it here or after you define the code as it's given here with a new name. And then if you run, sorry, if you run just with the inputs, Dask, of course, it's blazing fast because it didn't do any computation until and unless you call dot compute. So only when you pass on, let's just keep using time instead. Compute said it's not defined. Okay, yeah, it was running in a benchmark. Yeah, sorry. Okay, nothing happened here, probably a few milliseconds, but here. Now something flashed in the task graph. So there was some computation being done, and then now it's longer because as we've seen before. So even with the simple function, which takes in arbitrary input and does arbitrary work, you can use Dask and build up a graph. Let's try to see if this graph was something useful or it was just a, yeah, so it tries to do something smart, like it tries to build on top of these delayed operations. First increment, decrement, and then add it together and you get the results. So you can imagine not thinking about how to parallelize it. You do it as you do it in Python, but you still get parallelized work through Dask. Here is a note on like what kind of scheduler you should choose, because array and data frame are computation heavy. I'm not sure if this is correct. So you need to recheck this. I would go with processes as well with arrays and data frame, but I don't know. But anyway, you can swap between processes and threads just before a computation or with a context manager or setting it for the whole rest of the code by using this config.set. If you're familiar with Spark, Spark is a library built in Java with bindings with Python. So Dask has a lot of similarities in Spark, but as opposed to Spark, Spark is a very big giant library. You can either use Spark or not use Spark, but Dask is meant to, work together with other packages in Python. So that's why Dask has been very successful. Um, And Spark has support for Python as well as Dask, so there is no difference there. But Spark is more tuned to use data frame like work or big structured data. So that's where it fits in more. But Dask, as you see, even with delayed, you can use arbitrary functions and parallelize it. Both of them scale to cluster level computation. Um, but Spark, I don't think you will get much performance if you run it in your laptop. Um, so Dask has an abstraction for NumPy, whereas Spark doesn't. So you might be able to use Spark for something which looks like SQL or data frames. So that's why you get operations like map, reduce, group by in Spark. PySpark is the name for the Python binding for Spark, but they are not really useful if you're doing other things than data frames. Now on to the last exercise. We'll take 15 minutes. The objective of this exercise is to play around with the task delayed. So you can either the easiest way is to add at the rate Dask dask.delayed on top of this function and to see what's going on, like what do you get, and try to add compute. Don't forget to add compute to get the result, and see what happens in the dashboard. The other exercise, the second one in this set, is a bit more applied. You will have to download some netcdf files from the HPDA, the course content. Under content or data, you'll find it, or you click this link. And then what Xarray features is if you pass Xarray parallel equal to true, then automatically in the background it will be a Dask array. And then it makes use of the existing Dask cluster to parallelize things. So you can first try by loading the Xarray dataset using this, and then explore what these expressions give, like how you can analyze what it's doing. And of course, it wouldn't do any computation until you ask dot compute, as you do it in Dask as well. All right, welcome back. Don't worry if you didn't manage to finish everything, but just for the sake of completeness, I'll show how those two exercises look like running on Jupyter. So the easy way that I did was just to add these decorators. The other way would be to call using dash delete here. And then you see that the computation is happening in a lazy manner. It builds up a big task graph, which you don't have to worry about it. Dask takes care of it. And when you call compute, it does sum based on whatever the components of this list are based on these conditions. So even if you have branches within a loop, Dask will parallelize it for you, which is sometimes tricky to do it yourself by hand. The other one was to use Xarray and netcdf files. So here in the HPDA Python Git repository that I have in my file system, I changed the directory to content. There are some bunch of netcdf files which are opened using Xarray open multi-file dataset, which can take a pattern, and when you pass parallel equal to true, it will be a Dask dataset. So the only thing it will read in the beginning is the metadata, which is the dimensions it has, what the coordinates are, but all the data will be kept lazy because Xarray knows that, and even Dask knows that these are going to be heavy. So, but they will prepare some sort of chunk size for you based on the dimensions, how big the array is. And when you use multi-file data set, it will be combined into a single data set out of all these netcdf files. You can look at what a particular data is. Here it is temperature, and you'll see how it's split based into chunks. You can do some computation lazily. Here we are converting from Kelvin to Celsius. And even when you call mean, everything is kept lazy until you trigger some sort of computation. So you can look at either X-array data array or the underlying Dask array by calling dot data. So I tried to visualize the graph but it's too big, but you can see it's divided in a very big way. But when you call either compute or plot, it knows that it needs to actually fetch the data and does it for you. So with that colorful note, we come to the conclusion of this Dask episode. I hope you got a gist of what Dask can do. If you want to explore Dask further, you can play along with these exercises, or there is some more exercises in this optional material. So you can have a look at that to see how Dask can be modified even further. Try and different schedulers. Yeah, with that, over to you, Younglei.
Thank you, Ashwin, and thanks for the teaching. I would like to say a few words about the summary of this workshop. First, thank you so much for your participation and for this workshop on high-performance data analytics using Python. We mentioned a lot of concepts about scientific data format, efficient array computing, parallel computing, benchmarking, code optimization, and the Dask for scalable analytics. But I also mentioned that due to the time limitations, we cannot cover all as this aspect. Therefore, we provided more lesson materials in the optional lesson part about the parallel programming, GPU programming, and you can, if you like, you can go a step further with these lesson materials. For the participant, you access to Lumi, you can use it today or tomorrow, but make sure that once you finalize your accesses, you should fetch your data to your local computer. Otherwise, probably later you cannot access to Lumi. Next week. And the second, acknowledgement to my colleagues, Ashwin, Chang is here, and also Francisco. Thank you so much. For the lesson materials that Hackney document, everything is here. You can come back anytime for self-learning. And for the recorded video, we will upload to our YouTube channel. So I will send you a link to this recorded videos so you can follow the video and the lesson materials for self-learning later. At last, I would like to ask everyone to do us a favor and fill out the form. I will send it to you in the follow-up email this afternoon. And one thing, if you would like to get a certificate from me, you can reply to my email and I will send the certificate later. I mean, later means the Friday next week, before the Friday next week, because I will take time to collect this info. And yep, I think 1 minute past 12. Thank you so much for your participation. Enjoy programming and enjoy your days. Thank you. See you next workshop, hopefully.